Continuing section 5.3, applying Newton's laws, we're going to take a look at a sample problem or an example. It says a block of mass big M is 3.3 kilograms, connected by a cord and pulley to a hanging block of mass little m is 2.1 kilograms, slides across a frictionless surface. What is the acceleration and tension in the cord? And conveniently, they give us a picture, which is really great. So we have this frictionless surface with the sliding block of big M mass, and then there's the cord connecting to a hanging block, H. Right, so as we're going through this, we know we've been given the masses, but we don't have a whole lot more to go off of. But anytime we want to think about acceleration and tension, those are forces and acceleration. So that gets me thinking about Newton's second law, F equals ma. In order to use Newton's second law, we're going to need to identify all the forces acting on our bodies of interest. So I'm going to suggest we look at both the sliding block and the hanging block of what are the forces acting on them. So we can start with the hanging block. What are the forces acting on it? Well, actually, I want you to think about it for both blocks. See if you can fill in the forces that are acting on them on your own page, and then we'll compare notes in just a moment. So go ahead and pause the video and draw in the forces yourself. Right, did you do that? Well, for the hanging block, we're going to have the force of gravity that is pulling it down. So that would be one of our forces, F sub g. And then it's connected to this cord, so there's going to be tension. Tension is always a pulling force, so tension is going up. And it's not in contact with the wall, so there's no normal force here. Don't have to worry about friction. Similarly for the sliding block, because it's a frictionless surface, we don't need to worry about friction there either. But it is connected to the cord, so we're going to have tension. But in what direction? Right, it needs to be along the cord. And I'm just labeling it with a T because the tension is the same in either because it's connected to the same cord. Right, other forces, we still have the force of gravity on it, pulling down. And in this case, the force of gravity is not the same. So rather than using F sub g, since we don't have a convenient subscript, I'm going to switch to writing it as capital M times g. And similarly for F sub g over here, I'm going to switch to writing as little m times g. That should keep it clear. All right, any other forces on the sliding block? There's also the normal force. Because it is in contact with the surface and being pushed down into it, there is this normal force that is pointing perpendicular to the surface, which in this case is straight up. Right, so this is looking really solid. The only other thing I like to add here, and they've already somewhat done it for us, is what way we expect the blocks to move. So we expect that the hanging block is going to pull down and the sliding block is going to slide to the right. And so conveniently they have these arrows. They've already filled that in for us, but it doesn't hurt to have that extra detail. And so we see that we have the forces identified. Our work matches what's in here. They just added an S versus an H for sliding versus hanging. That's a lot of subscripts to me. And then I'll just note that if the blocks are moving in this way, assuming they aren't at a constant speed, which is going to be really hard when something is falling down, they're going to have some acceleration, A. And so I like to fill that in as well. And you could draw it next to each of them. There's an acceleration to the right for the sliding one, and acceleration down for the hanging one. And because the objects are moving together, it's going to be the same acceleration, A. Right, so this is a good start to getting us all set up. Now, let's look at an overview of what we want to do in order to solve this problem. So first, draw the forces involved. Check, we did that. Treat the string as unstretchable, the pulley is massless and frictionless, and each block is a particle. Also did that. That allows us to say that the tensions are equal. So we're good. Draw a free body diagram for each mass. So that's where we take the forces that were drawn on the previous page and draw them in free body form. So that's shown here, where the blocks become a single dot, and then we draw in these force vectors as pulling on the block, even if it's a pushing force. The other thing that this adds in, which I really like, is it shows that acceleration that we identified. That for the sliding block, it's accelerating to the right. For the hanging block, it is accelerating. So we're going to apply Newton's second law, F equals ma, to each block. Two simultaneous equations. We can eliminate the unknowns, they're the same, and solve for the acceleration. Right, so this sounds like a really solid approach. So I say we give it a shot. So I'm going to stop sharing for a moment so that you can see my screen a bit better. And I'll recopy my free body diagrams. For big M and little m. We have the normal force up, big mg going down, tension to the right. For little m, we have tension going up, and little mg going down. We could fill in our axes, which we can keep our classic x is horizontal and y is just vertical. And we'll keep up to be the positive direction. All right, and the last thing I'll put in here is those accelerations as mentioned. Sorry for the slight glare there on the screen. I think you could still see it though. All right. So now we're going to apply Newton's second law to both of these. So we can start with big M, Newton's second law, and we're going to do it in both the x and the y direction because it just doesn't hurt. So in the y direction, notice our forces are the normal force and the force of gravity. Fn mg, normal force is in the positive y direction, mg is in the negative y direction. And then we can plug in the mass is our capital M, and we're going to have to fill in the acceleration. How much is the sliding block accelerating in the up and down direction? You're right, it's not, right? Notice it is sliding and accelerating to the right, but for it to accelerate in the vertical direction in this case, it would have to either be sinking into the table or flying off of it, floating off somehow. The acceleration in the y direction for the sliding block is 0. And this tells us that the normal force is equal to the weight of the sliding block. And for this problem, that isn't very helpful because it doesn't ask us what the normal force is. What we will see is this becomes very useful when we're solving for problems involving friction. So stay tuned on that. But we can also look at the net force in the x direction. F net x is equal to mass times acceleration in the x direction. Still doing it for big M. So the only force in the x direction is tension. And that is in the positive x direction. So positive t is equal to capital M, because I'm plugging in, this is related to my big M. And then my acceleration in the x direction is just a. It's in the positive direction. So multiplying by a positive a. Okay, so there we have the tension is equal to big M times the system acceleration. All right, I don't know tension or acceleration, but that's where maybe the hanging block might help weight me out. So we can look at the net force in the y direction, because why not? But also because it is the only direction we have forces. It's equal to mass times acceleration in the y direction. And I like to write it out every time just to help myself focus on what I'm plugging into and to show my work. That's a good way to get partial credit. So forces in the y direction, I have tension and little mg. Tension is in the positive y direction, whereas little mg is in the negative. So I need to put in that negative sign there. And that is equal to little m that I'm plugging in. Now what about the acceleration? Notice there is acceleration in the y direction. We have to be careful before we just plug the a in. Is the acceleration in the positive y direction or the negative y direction? It's in the negative y direction. So this is going to be a negative a. That is one of the details that is the easiest to miss when solving these problems. So we now have another equation that has tension and the same acceleration. We have two equations, two unknowns. We can now eliminate one of the unknowns to solve for the other. Right? So if we want to solve for tension first, I can solve this top one for tension. T is equal to, I'll add the mg to the other side, little mg minus little ma. So if we set these two equations equal to each other, right, because tension is equal to tension, then we can plug in big Ma is equal to little mg minus ma. Now we have one equation with one unknown. Acceleration is our only unknown here. So we need to get the acceleration terms on the same side, so I'll add the little ma to the left. So I have big Ma plus little ma is equal to mg. And now I can just factor out the acceleration and divide by the total mass, and we will be home free. So A times big M plus little m is equal to little mg. And in other words, the acceleration is equal to little mg divided by the total mass, big M plus little m. That got a little low there, sorry about that. And so at this point, we can plug into our calculators. We know all two of the masses, little m and big M, and g is our positive 9.8 meters per second squared. So let's go back to, one other thing. That will allow us to solve for the acceleration. What about the tension? Well, once we know the acceleration, we can figure out what the tension is, right? Using either of the two equations we have for tension. So tension is going to be big M times our acceleration. That's one way we could write this. So I could write that my tension is equal to big M times little m times g, all divided by the total mass. Big M plus little m. Right, so now let's go back to the slides and compare with what we have there. All right, so we applied Newton's second law to each block. We eliminated the unknowns that are the same and solved for the acceleration. So we got the same equations as them, and combining them, we got this equation for acceleration and this one for tension. So if you plug in, you should find that the acceleration comes out to 3.8 meters per second squared, and that the tension comes out to 13 newtons. Now, an important extra step here is, does this actually make sense, right? So to check if it does make sense, what you want to do is you want to then think about different things. Do the units work out, or the dimensions? We can check our acceleration. We have mass divided by mass. And so sure enough, and then times acceleration due to gravity. So the masses cancel, we get the units of acceleration. Whew, that works out. Over here with the tension, most of the masses cancel, but we have one mass left times the acceleration. That will give us units of newtons, force. Awesome. We can also check that the acceleration is less than g, right? If we get an acceleration that's greater than 9.8, then there's either a rocket pack on these blocks or we made a calculation error somewhere. So the magnitude should be less than g. If we get a negative sign, that's usually just a sign that we we guessed the wrong direction of acceleration, but it also could be an error. We also should check that the tension is less than the weight of the hanging block, because if the tension was more than the weight of the hanging block, then the hanging block would be flying upward, which we don't have a source for why that is. We can also check some limiting cases. What if we turn off gravity? Well, if we turn off gravity, the acceleration becomes 0 and the tension becomes 0. Okay, that's a good check. What if the big mass, the sliding one, becomes 0? Well, in that case, let's see. We have our acceleration. If the big mass is 0, then the little masses would divide out and our acceleration would just be equal to g. In other words, the hanging mass would just be in free fall. That makes sense, because if there is no big mass, then it's like we've cut the rope and the hanging mass is just able to fall. Yeah, and the tension would be 0, similar to if we cut the rope. We could also check what if the little mass is infinitely big. Well, that starts to get a little weirder, but that's another important limiting case here, right? Where you can check all of these different results to try and make sure that things do, in fact, make sense. And going back to the little m is equal to infinity, I just wanted to think about for a moment because it's weird. If we have little m divided by big M plus little m, this addition, that added one's going to be nothing. So it's basically infinity over infinity. So the acceleration approaches that of gravity. That balances out. And the tension is a little more complicated. The bottom denominator will just approach being little m, becoming infinitely big. But in the numerator, because we're multiplying by a small number, it becomes something smaller, right? You could, for extreme example, you could make big M a fraction and make little m a large number, like 1,000,000, and then divide by 1,000,000 if big M's like 0.01 or something. That's going to disappear in the denominator. The numerator is going to be much smaller than the denominator, and so the tension will approach 0. So if the hanging mass becomes big enough, then it's like there is no sliding block. You don't even notice it. It's just that hanging block is going to be fallen and accelerating in free fall. So this pulls us through the end of this example.